actually also thank you very much for highlighting at Usman's presentation already my motivation of the paper. And thank you, Usman, for introducing most of the concept which I will also need. My name is Kasimir. I did my PhD with Andre Bormann and am now postdoc at ETH with Catherine DeWolf at the Circular Engineering for Architecture Lab. I think I can skip this introduction and motivation slide. We have heard it in this session quite often. Why do we need a circular economy? We have a huge amount of waste in the construction industry. We have a huge resource demand. And one of the solutions are circularity assessment in early design stages. So when we're designing new buildings, that we assess circularity and improve to close the linear economy to a circular one. And one of the challenges is actually calculating disassembly potential. So we heard about circularity indicators, building circularity indicators. I'm using the term disassembly potential because it's actually the term Domishevich used in her very early work when she defined how to calculate disassembly. In industry, it's often also called detachability. And Van Vliet showed it in one of, this is also adapted from Domishevich. He showed how this is actually calculated. So usually you have this section of a detail of a wall and a window. You have different nodes of elements or material layers, or I will call them layer composites or components. And they're somehow connected. They're connected to each other in a quite complex manner. And the properties which you need to calculate this assembly potential, Domishevich and then Van Vliet defined here as follows. And you can see that there are properties in the nodes and in the edges between the nodes. So this is quite detailed somehow in industry. Also, if we are looking into integrating it in BIM, we have stored these information not in the edges, but mainly in elements. So not on layer or material level, but for the whole element, which is quite imprecise and very simplified. So I actually want to enable the usage of BIM models. So there's already BIM-based enrichments. Here's a publication with a colleague from 2 weeks ago with these details of the left side, but including it to building information modeling. So the research question I want to tackle in this conference paper is how can detailed information for calculating disassembly potential be formalized using BIM models in early design stages. So how can we actually enable also architects, planners to automatically get a first results on these assessments and then optimize the results with making more smarter or better decisions regarding to the disassembly. And the hypothesis is I'm also using archetypes on element level with quite detailed information. I'm actually going to use Totem database, which has quite a lot of relevant information to calculate disassembly. It's a Belgium database. I'm using a graph representation where I'm actually using these different representations of the Totem database and BIM models. And I know there are a lot of ontology people at this conference at least, and I didn't decide for ontology because I want to do actually an interactive decision making, also for visualization, and I think calculating it iteratively is then, I decided for labeled property graphs for this disassembly potential calculation for decision making. So the workflow looks as follows. We have a BIM model. Usually we have actually the IFC already exported. I tried to reduce actually also the exchange requirement to just base quantities, materials, and space boundaries. Then we have these element archetypes. As I said, I'm using Totem. I need to restructure it a little bit because some information are missing. So I'm manually enriching it in this paper, but later I want to automate this too. And then we have the graph processing. So we have an IFC graph. As I said, labeled property graphs, I will represent it in Neo4j. And the archetype graph is also transformed to a Neo4j. And in the end, we're matching the elements of the BIM model with the archetypes, which are more detailed than in the BIM model. In this paper, we're doing it manually, but in the follow-up paper, we're trying to automate it, which is out of scope here. And then we're actually fusing this one graph, so we have a kind of a disassembly graph. I know Zain, my colleague, presented yesterday a different type of disassembly sequencing graph, which is more like at the end of the manufacturing to disassembly. This is more like the disassembly potential graph. And then we can actually calculate disassembly potential on element-specific levels in the relationships in the nodes of the components, in the elements, and then aggregate it for the whole building. This fused disassembly graph model looks as follows. In blue, we have the IFC graph somehow with spaces, elements, materials. With a certain logic from the IFC representation, we know how the material layers are connected and how the elements are connected to each other. On the right-hand side, we have the more detailed archetype graph. As I said, I'm using Totem. These are the information given in a Totem database. Then we manually match it, so there are some manual steps involved still here. However, using graph representation, we can, for example, automatically calculate the type of a relational pattern, which is one property. How often is one node connected? So we use the graph representation to automatically get the properties too. And in the end, how are the different layer composites connected? For enriching the element connections, I'm using IFC rel voids element, so how which openings, windows or doors are connected to which walls. Rel connects path elements, how are the walls, in which order are the walls connected to each other, and then I also use space boundaries, first level space boundaries, to see which other elements in the room are connected to the room, and then we always usually know the slabs are connected to the walls, and the roofs are connected to the walls, so we in the end know exactly for the relevant IFC elements how they are connected to each other. For the totem composite connection, we make some assumptions, some domain-specific assumptions on the directionality. So we say the load-bearing element or component is the one which is built first, and then the other ones are attached to it. And that's how we can see here on the right-hand side the directionality of the connections comes in it. We applied it to a very, very, very simple case study. So it's just a one-room case study created in Revit. To keep it very simple, also to understand if the graph is correctly fused and aggregated and calculated. In the ongoing research, we are now applying it to actually real-world case studies, and the graphs are getting more complicated. So we have the IFC graph on the left. We selected manually the according archetypes, element archetypes from Totem database, and also transformed them to Neo4j or to labeled property graph. And in the end, we fused these two graphs together using the model I showed before. And then actually this is one example of the roof, quite detailed roof. The IFC model had, especially in early design phases, not that many details, especially not in this geometric precision. So we maybe had 2 or 3 layers in the BIM model. Here we have 9 different layers or materials. And then if we look at in more detail, this is the detail of this. On the right-hand side, in green, you see the IFC element, and in small dots, small nodes, you see the IFC materials, and on the left side, you can see actually the more detailed archetype graph. But you can also see that in orange there are the connections to other components, component level components of the other elements. So we don't just connect elements to each other, but actually every layer composite or every component to each other. So how does this help now the architect or the designer? We also developed now an interactive visualization where we actually fuse the IFC model to navigate. It's easier to navigate, but as you can see on the bottom, it's the full disassembly graph, which is impossible to navigate in. So if you actually then click on an element in a moment, then you can see that it actually gets filtered down. You have then in gray the IFC graph, and the nodes in blue are the disassembly information. It's interconnected, and I'm coming to the end. This is ongoing research, so this we want to test then with real-world case studies and architects. The limitations, of course, I said, manual matching. We're working on this currently. We also made some assumptions, but of course it's more detailed, the representation as we have today in the current tools or BIM models. And we want to actually overcome this manual matching with an LLM-based element matching method and test it on real-world case studies. Thank you very much for your attention, and I'm open for questions.